Section 1.6 contains several examples of applications of linear systems. We're only going to look at one, and we'll work through this exercise here that's on a handout posted, a PDF posted in Canvas. It's an example of a network flow. So the diagram below shows traffic flow on several one-way streets. So notice these are one-way streets in a city, and we want to determine the general flow pattern for the network. So what we got to do in this problem is determine the values of x1, x2, x3, x4. They're like the unknowns we have to solve for. And the way you read this diagram is these numbers that are labeled. So over a certain period of time, I don't know if this, it could be an hour or we don't know exactly what, but it's a certain fixed amount of time. 200 vehicles drive along this one-way street along this block toward intersection D. So D is the intersection of two streets. And 600 drive away from intersection C. And then we also have this 500 and 700 amount labeled. Oh, and we got 400, 400 here, and 600 here. So we have a certain amount of cars driving into the system, driving out. And we want to figure out what does this mean about x1, x2, x3, x4. How heavy is the traffic on those four blocks? Now, real examples of network flow will involve, say, a much more complicated system. Say it could be a map with hundreds of streets on it and hundreds of possible values to be determined, and this would be a huge system that would be solved by computer. So this is a simplified version, but it's a real life example of a linear system situation. So let's go ahead and set this up and solve. And again, notice these are one-way streets, so like Maple Avenue all the way through, even the X1 portion is one way going right to left, while Elm Avenue is going left to right is the traffic flow. So what we're going to do is we're going to look at each intersection. We're going to set up an equation. And the only principle we're applying here is flow in equals the flow out. That's how we're going to get an equation in each case. So we have intersections A, B, C, and D. So A, B, C, D here. And at intersection A, we have, let's see, flowing into A is x1 and x4. So the flow in is the x1 number of cars plus x4. And there's only one way out from intersection A, so the flow out is 700. And for B, the flow in is 600 plus 400. And that's got to equal the flow out, which is x1 plus x2. For C, the flow in, let's see, is x3 plus x2. So x2 plus x3. And the flow out is 400 plus 600. And finally, at D, flow in is 500 plus 200. And the flow out is going to be x3 plus x4. So those are our four equations for this system, and these can all be rewritten, right? The first equation I can rewrite as x1 plus x4 equals 700. I guess that's just the way I wrote it. Whoops, 700, not 7,000. Second equation, I'm going to write the variables on the left-hand side to follow our standard setup for a linear system. So I can write x1 plus x2 equals 1,000. 600 plus 400. Equation C is x2 plus x3 equals 1,000. And the fourth equation, D, x3 plus x4 equals 700. And so we want to solve this system. And we'll apply our augmented matrix process, our Gaussian elimination. So for this system, let's see, I'm going to have coefficients of x1 are 1, 1, 0, 0. Coefficients of x2 are 0, 1, 1, 0. Coefficients of x3, 0, 0, 1, 1. Coefficients of x4 are 1, 0, 0, 1. And then my constant coefficients on the right are 700, 1,000, 1,000, 700. So this is not a hard system to solve in any way. It's just, so to me, it's mainly just interesting to set this up, get to the end, and then we got to talk a little bit about what the interpretation would be here for this. There is a little bit amount of work in reducing this to reduced echelon form. Let's go through some of these steps. So I got a pivot position up here in my upper left. I want a 0 below, so I'm going to take row 2 and replace it with row 2 minus row 1. What do we get? We have 1, 0, 0, 1, 700. And now I'm going to take row 2 minus row 1. So I get 0, row 2 minus row 1 is 1, 0. I'm going to have 0 minus 1, so a negative 1. 1,000 minus 700 is 300. 0, 1, 1, 0, 1,000. 0, 0, 1, 1, 700. So my first column is set up. I got my pivot with zeros below. My next pivot will be here. I want zeros below. So I'm going to replace, not row 2, row 3 is the row I want to change. Row 3, I'm going to replace with row 3 minus row 2. And what do we have? So recopy, and now row 3 minus row 2. So 0, 0. Row 3 minus row 2 will be 1. Now I have 0 minus a negative 1. I'm actually going to get plus 1 here. And I'm going to have 1,000 minus 300 is 700. And actually my second row is all set up now. And I guess let's go ahead and just work through this now. I got pivot, 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 and I want a 0 below. So row 4 I'm going to replace with row 4 minus row 3. It's a minus sign. I think we're just about got this in reduced form. Let's see. Zero, 0, 1, 1, 700. And now we're going to make a change here. We're going to take row 4 minus row 3. So we have 0, 0, 0, 0, and actually I get another 0, right? I get a row of zeros. And so I think this is now in reduced echelon form because I have 3 pivots. Three pivot columns. My fourth column is not a pivot column, so there's a free variable at x4. And let's sum up what we got on another piece of paper. So I have x1 plus x4 is 700. I have x2 minus x4 is 300. And I have x3 plus x4 is 700. And x4 is free. So let's go ahead and write this solution in vector form, since that's what we always do. So my general solution will have 4 components. And let's see, x1 is 700 minus x4. x2 is 300 plus x4. x3 is 700 minus x4. And of course x4 is free, so we write x4. And so in vector form, I can express this as a constant vector, 700, 300, 700, 0, plus x4 times the vector negative 1, plus 1, negative 1, plus 1. And now normally when we solve, we say where x4 could be any real number for our general solution. But here, just notice there are lots of possibilities, so our network flow has more than one possible situation. We can say it all kind of depends on how many cars end up flowing along just one of these blocks, right? That will determine the other 3. So if we know x4, it determines the other 3. But here, for instance, certainly x4 cannot be negative. So we can't say any real number, right? We can't have a negative. And I think there's also a maximum value for x4. So x4 is the flow out of, part of the flow out of intersection D. 3 is a flow, x3 is flow out. The only flow in is 500 plus 200 is 700. So I believe x4 has to be less than or equal to 700. If all the cars took the x4 block, it would be the largest possible value we could get for x4. So a little technical point, don't get all worried about that. But again, this would be way more interesting if we had a huge system with many equations, many intersections, and many cars involved. But there's our solution to the problem that started out looking like this. And our solution ends up looking like this, right, to that network example. So we're going to look at one more application. It is a totally different kind of application of linear algebra. And that will come from section 110. This is the only application we're looking at from 1.6.